What is the calculated heat of mixing of 1000 grams of polystyrene with 1000 grams of polybutadiene? If the molecular weight of both polymers is on the order of 1 times 10 to the power of 5 grams per mole, would you anticipate that the two polymers are mutually miscible at 150 centigrade? What are the experimental results in this case? So the enthalpy of mixing delta Hm is given by Kt, where K is Boltzmann constant and T is temperature, times V over Vr, where V over Vr is the count of the number of cells in 1 centimeter cube or per unit volume, and V is the volume of the sample. Small v1 and small v2, which are the volume fractions of the two polymers, chi12, which is the Flory-Huggins parameter for the given solute-solvent combination at the given temperature, times 1 minus 2 over z, where z is the lattice coordination number. We have to find out V, which is the total volume of the sample. Total volume of the sample is equal to volume of polystyrene plus volume of polybutadiene, which is mass of polystyrene is 1000 grams, so that over the density of polystyrene, which is 1.06 gram per centimeter cube from table 3.2, plus mass of polybutadiene is 1000 grams over the density of polybutadiene, which is 1.01 grams per centimeter cube. So if we add these two, we get 1933 centimeter cube as a total volume. Let's calculate the volume fractions V1 and V2. Volume of polystyrene is 1000 grams over 1.06 grams per centimeter cube. That over the total volume of 1933 centimeter cube is the volume fraction of polystyrene, which is 0.49, and for polybutadiene it is 1000 grams over 1.01 grams per centimeter cube for the density over the total volume of 1933 centimeter cube, which is 0.51. Chi is given as V1 over RT times delta 1 minus delta 2 whole square, where delta 1 and delta 2 are the solubility parameters of the two polymers. And from table 3.2 we see that delta 1 is equal to 9.1 square root of calories per centimeter cube, and delta 2 is equal to 8.4 square root of calories per centimeter cube. V1 is the molar volume of the solvent, and the molar volume of the solvent is 1 mole of polystyrene, which is 104 grams per mole, over the density, which is 1.06 grams per centimeter cube, which is 98.11 centimeter cube. So chi is, by plugging in the values, 98.11 centimeter cube times 9.1 minus 8.4 squared calories per centimeter cube over 1.987 calories per mole Kelvin times 423 Kelvin. So that is 0.057. V over VR, V is the total volume, which is 1933 centimeter cube times 6.023 times 10 to the 23 molecules per mole over the molar mass. We can take the average of molar mass of polystyrene and polybutadiene, which would be 104 plus 56, 160 over 2, which is 80. So 80 grams per mole. Density of polystyrene is 1.06 and that of polybutadiene is 1.01, so it's 2.07 over 2. So the average is 1.035 grams per centimeter cube. So that times the average density, which is 1.035 grams per centimeter cube. So it's a total volume times the average density over the average molar mass. Plugging in the values, delta HM equals 1.38 times 10 to the negative 23 for K times 423 for the temperature times V over VR is 1.5 times 10 to the 25 times the volume fractions V1 and V2 are 0.49 and 0.51 times chi12 is 0.057 times 1 minus 2 over 6, where 6 is the Z or the lattice coordination number. At the point when the two polymers become miscible or immiscible, delta G M will be equal to 0. We know delta Gm equals delta Hm minus T delta Sm. So delta Hm is Kt times V over Vr times V1 V2 chi12 1 minus 2 over Z, and delta Sm equals Kt times Nc V1 ln V1 plus V2 ln V2. Nc is the number of polymer chains per unit volume. So we want to find out the point at which delta Hm becomes equal to minus T delta Sm. So the point at which Kt V over Vr V1 V2 chi12 1 minus 2 over Z becomes equal to Kt times Nc V1 ln V1 plus V2 ln V2. We can cancel Kt from both sides. So the number of polymer chains per unit volume NC would be V over VR V1 V2 chi1 to 1 minus 2 over Z over V1 ln V1 plus V2 ln V2. Now the molecular weight at which the chains become immiscible will correspond to the chains having NC number of chains per unit volume. So the number of mers per chain would be V over VR over NC. So that would be V over VR over V over VR times V1 V2 chi1 to 1 minus 2 over Z over V1 ln V1 plus V2 ln V2. So we get number of mers per chain as V1 ln V1 plus V2 ln V2 over V1 V2 chi1 to 1 minus 2 over Z. If we plug in the values, this would be 0.49 ln 0.49 plus 0.51 ln 0.51 over 0.49 times 0.51 times 0.057 times 1 minus 2 over 6. That gives us 69 mers per chain. Since the average molar mass is 80 grams per mole, a molecular weight of 80 times 69, which is 5520 grams per mole, would be the point at which it becomes immiscible. So anything molecular weight higher than 5520 grams per mole would be immiscible. Which means the given molecular weights, which is 1.10 to the power 5 grams per mole, would be immiscible at 423 Kelvin.